So in the last class, we were discussing this Strassen's matrix multiplication algorithm, and some of you raised the question that if it is not the exact power of 2, say we had an example, say 4 by 4, 4 by 4 I am having, and then if it is 3 by 3, then what will happen? Who raised the question? You there? Okay, so this thing I can address little bit later when all of you will be joining. Okay, so today the first part we will be dealing with this recursion tree, and the next part we will start this greedy algorithm. Okay, so for this why this recursion tree is needed for solving recurrences. Okay, we have already seen one idea of solving recurrences, that is called substitution method. In other books, substitution method is differently presented, but as far as this CLRS is concerned, substitution method is this, and the central idea is we have to guess a solution, and then we have to verify. So verify that whether our guess is right or wrong. Okay. So this is the technique we have utilized for this substitution method. Now whenever we have got a recurrence like this, Tn equal to 2Tn by 2 plus n, say, then say we are guessing, say I am guessing that the solution is Tn equal to order of n log n, and the obvious question that will be coming to our mind, that how to guess. Okay, so this is the central question. How to guess. Whenever I am seeing, say this is a known recurrence, but if I see some kind of little bit awkward looking recurrence, then how to guess a solution, right? So that is the central question. To answer this question, we use this recursion tree. Okay, so this recursion tree will be helping us. This recursion tree will be helping us to guess, a solution, in substitution method. Okay, so that is the main idea for with which this recursion tree is introduced in CLRS book. Okay? In this CLRS book, and you know this document is from that CLRS book, straight away from CLRS book. Okay, so say we have got a recurrence like this, Tn equal to 3Tn by 4 plus theta n square. If I have got a recurrence like this to be solved, then what we got to do, first of all, first thing is that we have to omit this annoying floor or ceiling, whatever we are having. So that will not be affecting too much to the recurrence. Okay, so this recurrence is, you see, after omitting that, it is boiling down to this recurrence. Okay, this recurrence. This is we say in the parlance of solving recurrences that we are allowing some kind of sloppiness. Okay, some kind of sloppiness we are allowing. So the first thing is that we are omitting floor and ceiling, right? and then we will be having a little bit from that awkward looking recurrence, we are getting a much more cleaner recurrence form. Okay. And then we have to apply this recursion tree to guess the solution of this. Okay. So in recursion tree, okay, so before that, one thing that will be necessary in our subsequent that means subsequent lectures, so we should say, because this is a very central notations that we are having here, right? Central formula rather. So here this, if x not equals to 1, so this summation k equals to 0 to n x power k, right? X power k, that means if we expand this this one, then it is 1, k equal to 0, x power 0 is 1, plus x power 1 plus x square plus up to this x power n. Okay. So this is the series, and this series, you know, this is the geometric series, and the formula whenever we are starting from k equal to 0 to n. So the formula is x power n plus 1 minus 1 divided by x minus 1. This we use very often in computer science for analyzing algorithms. Okay. And this one also will be coming in this recursion tree method, okay, in our example. And also this one will be coming heavily, okay, in many different algorithmic analysis. So this series comes up, okay. So here little bit is changed from k equals to 0 to n, here k equals to 0 to infinity, and x power k, here x is less than 1, okay. So here this absolute value of x is less than 1, right? And if this is the case, this is the infinite series, right? And x less than 1, and then we are having a very nice cryptic formula that is 1 by 1 minus x. And that, as we do asymptotic analysis in computer science, especially whenever we are analyzing algorithms, then this is a great tool for analyzing algorithms, or in the computer science parlance, this is a very important tool. Okay, this is very important formula rather, because I am telling that this is a tool because it is having many different applications. Okay, this thing. One of the ways that we will be seeing that some bizarre looking expression is becoming a very short by using this formula, okay, today. Okay, so in the recursion tree, each node represents the cost of a single subproblem somewhere in the set of recursive function invocations. And then what we do is we sum the costs within each level of the tree to obtain a set of per level costs. Okay. So if I am having this, right? If I am having this, then n, this will be represented by first this Tn by 2, and then this Tn by 2. And then this Tn by 2, if I am substituting here n by 2, then it will be 2t n by 2. Instead of n, we have to put n by 2, and then it will be n by 4 plus n by 2. So if I am going another level, then it will be n by n, and then n by 2, and then this will be again subdivided into 2. So this is Tn by 4 This is Tn by 4, Tn by 4, Tn by 4. So each level cost, this will be n, this will be n by 2 plus n by 2. So each level cost we have to add up. So that is what it is told here. We sum the costs within each level of the tree to obtain a set of per level costs, and then we sum all the per level costs to determine the total cost of all levels of the recursion. So this way all level cost we have to add up, and then we will be getting the total cost. Okay. So instead of saying other things, let us take the example. Then you will be able to understand much more in a clear manner. Okay. So this is the previous recurrence, that Tn equal to 3t n by 4 plus order of n square, and that order of n square is upper bounded by Cn square. Okay. Cn square, right? So now this is the way that we have already I have already shown you that Tn equal to 2Tn by 2 plus n, how we will be decomposing it. So first is Cn square will be there, Cn square, and then it is 3Tn by 4. That means Tn by 4 plus then this Tn by 4, then this Tn by 4. So that is the way we have to represent. And then this n by 4 we have to substitute here. So if we substitute here, then what we are getting? Tn by 4 is coming as, so 3 T n by 4, that means n by 16 it is coming, plus C n by 4 whole square. So this is coming. So if I go one more level down, then it will be, we have to write Cn square is this. So this is coming from here, right? So this is Tn by 4. So Tn by 4 we have written in this manner, So that Tn by 4 again we have to write in this tree form. So C times n by 4 square, and then C times n by 4 square, then C times n by 4 square, and then we are having this again, this three branches living here. So you see these 3 branches having Tn by 16. So this is Tn by 3Tn by 16. So this is Tn by 16, Tn by 16, one I can write, and others you have to write mentally. Okay. And then one more level, if Tn by 16, if I am putting here, then we will be getting this thing. Okay. This thing. So this is the way we have to decompose this tree. We have to unfold this tree, okay, like this manner, like this way, right? And then what we are doing is we are summing up the per level cost. So here it is Cn square, okay? Cn square, that is written Cn square. So now it is written this is n by 4 whole square, means n square by 16. So C n square by 16, Cn square by 16, Cn square by 16. If we add this up, then it will be 3 by 16 Cn square. Okay. So like this way, if we add this cost, this level cost, it will be 3 by 16 whole square times Cn square. Now you see there is a nice pattern going on. Okay. So this is nothing is written here, that means 1 times this Cn square, 1 times this Cn square, then here it is coming 3 by 16 times Cn square. Then the next level we are having 3 by 16 whole square times Cn square. Okay, so we can write, instead of 1 we can write it is 3 by 16 whole power 0. Okay, so you see there's a nice pattern going on, and we have to find out this pattern. Okay, we have to find out this pattern. If I can find out this pattern, then my job is 60% done, and other things will be there for routine algebraic manipulation. Okay, so here these par level cost we are finding out, par level cost including the leaf levels. Okay, including the leaf levels. So whenever we'll be going down to the leaf levels, so at that time what we will be having? We will be having all size boiling down to 1, right? So T1, T1, T1 and all these things. Now it is written here that now the question is coming that how many nodes will be there in this leaf level. What we will be doing is, as leaf level we are sure that it will be T1, and T1 will be getting some constant cost involved. So leaf level we will be processing separately. Leaf we will be processing separately, leaf level, and other levels we will be processing separately. Okay, so that is the idea. So now this, how many nodes will be there in the leaf level, that we have to count, and then if we are counting, then this result we will be getting. So let us count this and then we will be coming back here. Okay. So it is written that it is boiling down to theta n log Lg or log. So this is log because this is not base 2, 3 base 4. So what is the value of log 3 base 4? Who will be telling? Log 3 base 4? Will it be less than 1 or greater than 1? Who? Less than 1. Okay. So you see, this leaf level cost is not even, this leaf level cost is not even theta n. Okay. Theta n means theta 1. It is less than this. Okay. So that we have to remember. So this leaf level cost we have processed separately, but still we haven't got the idea that how this n power log 3 base 4 is coming. Okay, so that we are discussing right now. Okay, so this okay, so this is the discussion here. Just wait. So because subproblem sizes decrease by a factor of 4. Okay, by a factor of 4 each time we go down one level. Okay, each time we go down one level. So first is C n square, then if I am going one level down, the subproblem size is becoming n by 4 from n. Okay, subproblem size. So this is 1 by n by 4, n by 4. Okay, so subproblem size, and in the next level it will be T n by 16. Okay, so it is again being decreased by a factor of 4. It's a factor of 4 we are having the the subproblem sizes are decreasing by a factor of 4 each time we are going down one level. So if we go like this, then eventually we must reach a boundary condition. And at that time the subproblem size will be 1. So if I go down, then at some point we will be hitting this T1 case. So then the question is, how far from the root do we reach 1? Okay. How far down the level we have to go to reach this one? So what we can say is, as it is getting decremented by a factor of 4, it is getting decremented, the subproblem size. So what we can say that, okay, so this is at this level it is n by, so at any ith level, what is the subproblem size? The subproblem size for a node at depth I is n by 4 power I. So as it is decremented by 4, factor of 4. So because you see this, if I equals to 0, so that is this level, root level, I equal to 0. So at that time 4 power 0, that means n. So it was n here. And then one level I am going down, then the subproblem size is becoming n by 4 power I, where I will be equals to 1, that means n by 4. Okay, so that is the case. If I go one level down, it will be n by 4 square, that is n by 16. This is the case. So at any ith level, the subproblem size will definitely be n by 4 power I. Okay, and whenever we will be reaching this leaf level, whenever we are hitting T1 case, this n will be equals to 1. That means the subproblem size will be equals to 1. So at that level, what will be this I? So at this time, I, the leaf level is also at any ith level. So which ith level? So at that time n by 4 power I, this is the subproblem size. This is the subproblem size of the leaf node. That will be definitely be 1. Okay. So if I am equating like this, then what we are getting? So this whenever we are doing this, then I will be equal to what? I will be equal to log n base 4. So this means n equal to 4 power I, and then so this log n base 4 will be equals to I, right? So at the leaf level, so I, that means we are at this point, this leaf level, what the I value is? Log n base 4. That means what we are telling, that means the height of this tree is becoming this. Okay, height of this tree is becoming this. And another thing, so how many levels we are having? We are starting from 0. So 0 to this log n base 4, these many number of levels we are having. That means log n, if 0 to n, that means n plus 1 number of levels. So 0 to log n base 4, that means n base 4 plus 1 levels we are having, right? So this is one thing. And another thing, so our job is still not over. Okay, so our job is still not over. And another thing that we have to take into account is that next we determine the cost at each level of the tree. So each level has 3 times more nodes than the level above. 3 times more nodes. So here if I am thinking at the root level, how many nodes we are having? 1 nodes. And at this level, how many nodes I am having? 3 nodes. So if I am expanding this, how many nodes we will be having? 9 nodes. So what we are observing is that each level has 3 times more nodes than the level above. Level above. And so the number of nodes at depth I, will be 3 power I, because this subproblem size is reduced by a factor of 4 for each level. We go down from the root. Okay? So this from that observation only we can say that the number of nodes at depth I will be equals to 3 power I. So if I equals to 0, it will be 3 power 0, that means 1. That is the root level. How many nodes we are having? If 3 power I, that is 1, that means the second level we are having 3 nodes. And then this 3 power 2, I guess this is so 9. That means at this level, how many nodes we will be having? So at any level I, how many nodes we will be having? These 3 power I nodes. So now with this observation, I can say that at the leaf level, at this level, how many nodes we will be having? So we simply put this I value there, because at the leaf level, I value is known. Okay. So at that time 3 power I, so leaf level, how many nodes will be having? 3 power I, where I will be equals to log n base 4. So if I am plugging that value, then it will be log n base 4. So now if I am exchanging this 3 and this n, then it will be n log 3 base 4. So exchanging this 3 and this n. Okay, so this is a famous formula. By using that we are doing this, that you know from the 12th standard. Okay, so this is the number of nodes we will be having at the leaf level. At the leaf level we will be having these many number of nodes, and each node contributing T1 cost, that means constant cost. So the leaf level cost will be, then it is written theta in log 3 base 4. So now it is clear that how the leaf level cost is coming like that. Okay, right. And what we have got, this the first level cost is Cn square, the second level cost is 3 by 16 Cn square. So all these costs we are adding up, and one as the leaf level is separated, so it will be how many? Log n minus 1. So that will be starting from 0 to this. So that is what so this thing we can write in a shorter form, in the summation form, I equals to 0 to log n base 4 minus 1, and then 3 by 16 whole power I Cn square. And this is here. Okay, and this is separated. This is not within the summation. Okay, because this is the leaf level cost already we have calculated. That is simply added up with this. So now you see this is the formula, this 3 by 16, this is our x. This is our x power I formula. X power I equals to 0 to some n, x power I times Cn square. Okay? So if I utilize that geometric series formula, x power this n plus 1 minus 1 by x minus 1, if I utilize that formula, here, that general formula, then we are getting 3 by 16, that is x power log n base 4 minus 1 plus 1. So this plus 1 will be coming, n equal to this log n base 4 minus 1. So minus 1 divided by this x minus 1, x is 3 by 16. So this will be the case. Okay, and this is a bizarre looking, this expression is a bizarre looking one. Okay, so then, so this, the last formula looks somewhat messy. Okay, that means a bizarre one we are getting. Now this until we realize that we can again, so you see this beauty here, until we realize that we can again take advantage of small amounts of sloppiness and use an infinite decreasing geometric series as an upper bound. That means from I equals to 0 to n, what I will be doing is I will be substituting that by I equals to 0 to infinity. Okay, as we are, just a minute, just as we are dealing with this asymptotic analysis. Okay, just a minute, just to show you this. Yes, it has come. So this, you see in the next line, what we are doing is, so Tn equal to this was there, and in the first step we utilize the direct formula. Now what we are doing is, we are taking the help of this asymptotic analysis and we are writing that this is less than this summation I equal to 0 to infinity 3 by 16 whole power I Cn square. I haven't done anything, just I have converted from this 0 to n formula to 0 to infinity formula, infinity summation. Okay, and that we can do because 3 by 16 power I Cn square, that what I am doing, I am adding few more positive terms there. So definitely this term will be greater than this. That means this will be less than this. Okay, so now you see we are done. Okay, so we have got this I equals to 0 to infinity 3 by 16, that means x power I. So this is x power I formula we have got, and this x is less than 1 here, x is less than 1. Okay, x is 3 by 16. So now this formula already we know that this is 1 by 1 minus x. So this will be 1 by 1 minus 3 by 16. Okay, so this will be 16 by 13 Cn square. That this from this, if I want to reach to this conclusion, it might be making your life hell. Okay, so that if I am taking instead the help of this infinite series formula, then our life will be much more easier. Okay, and then these are remaining the same, throughout. And now you see 16 by 13 Cn square plus theta n power something which is less than 1. Okay, so even if I am taking this is theta n and this is some 16 by 13 Cn square, that means it will be order of n square, theta n square, order of n square or theta n square. This is plus theta n, then definitely this is order of n square. This is order of n square, we can guess. So this Tn, we had this 3t n by 4, the expression was, this recurrence was 3t n by 4 floor, and and then this Cn square. So this, for this recurrence I have guessed. Now the solution I have guessed is Tn equal to order of n square. So the guess after doing this, the guess is Tn equals to order of n square. So this is the guess. So for guessing, I have utilized the help of this recursion tree, right? So now you have understood that why this recursion tree we have solved at length, and so that we can get a good guess. We can, instead of arbitrarily guessing, we have followed some systematic method by utilizing the recursion tree method, and we have got this. Okay, so this is how we have got a very powerful solution technique. This recursion tree is because this will be giving a very intuitive guess for solving through this substitution method. There is a technique with which recursion tree can be also utilized to get the exact solution, but here we are utilizing the power of recursion tree to guess a solution for the substitution method. Okay, so we have derived a guess of Tn equal to order of n square for our original recurrence, this. Okay, for our original recurrence, this. In this example, so this is not required. So this was the point. Okay, and now it is still not over. Okay, it is still not over, right? So okay, we have got a good guess, right? We have got a good guess, and so now we are having this Tn equal to 3t n by 4 floor plus theta n square. Okay, theta n square, this is the recurrence, and our guess is Tn equal to order of n square. So this is the guess, and now we know how to solve this by using substitution method. So we have to assume that it is true for this n by 4 floor. So then it is coming as T n by 4 floor, that will be equals to, so this is Tn equals to, this means Tn, we have to prove that this is less equal to dn square. It is dn square. So T n by 4 floor means d times n by 4 whole square. So we have assumed that this is true for this, and now we will be plugging the results. So Tn will be less equal to okay, so this is less equal by this, less equal to, so this Tn 3t, so d n by 4 floor whole square plus this theta n square upper bounded by Cn square. Okay, I am writing. So this is exactly this thing we have followed here. So this is the recurrence, and then this is our, we have got so far. So we have got this, okay, 3d, and now we are omitting this floor. Okay, so it will be, so this is we can write within bracket whole square. So this is this, if I am omitting this, so 3d n by 4 whole square plus Cn square. So now what we can do is 3 by 16 dn square. We have got n by 16, sorry, n square by 16 plus this Cn square is coming, and now you see I can write this as dn square minus, what I should write, Can anybody tell me? 3 by 16 dn square, and then I want to write dn square minus something. What I should write? Who will be telling? Tell me, tell me. Who is telling? Very good. And you see this, whoever is, what is your roll number? 8100 means 100. So each answer will be carrying some marks. Okay, each answer, whenever I am asking, each answer will be carrying some marks, and that will be added to your account. Okay, so that will definitely be taken care of. So those who will be listening carefully, they will be scoring some marks definitely. So the first assessment only will not be based on the written exam. That will be based on the performance of the class as well, right? Okay, so dn square minus 13 dn square, right? So now I can write, so this is dn square minus this 13 by 16 dn square minus cn square. So then I can write that this is less equal to dn square. When these will be definitely greater equals to 0. So if 13, we can solve 13 by 16 dn square minus cn square greater equals to 0. That means this 13 we can multiply throughout by say 16. So we can get 13 dn square minus 16 cn square greater equals to 0. That means then n square dividing throughout n square, so 13d minus 16c greater equals to 0. That means 13d greater equals to 16c. That means 13d. That means d greater equals to 16 by 13c. So here it is written d greater equals to 16 by 13c. One step they didn't do. From here to here, you have to do the manipulation like this. Okay. So d greater equals to 16 by 13c. If I am choosing whatever c I will be choosing d by multiplying 16 by 13, this c, and that liberty I am having. So this is dn square, and now I can say that our guess is absolutely right. Our guess is right. So it is absolutely in a right track. Okay. So I guess time is up today. Anyway, so this was the recursion tree, how to guess the solution, and then by using substitution method how to solve this. So now somebody in the last class asked this Strassen's matrix multiplication. Who asked this question? You will be having some marks there, so you come up. Who asked this question? That okay, this is exact power of 2, instead we can take this square matrix, and how to solve this? Who raised the question? Did you forget? Okay, so anyway, so this is, if this is a say 3 by 3, then what we got to do is we can add up, we can pad some zeros here, and then we can make it the exact power of this 4 by 4 and we can proceed. So that is the solution. Okay, so if you have any question you can ask me now, but have to, first of all I have to stop it